Okay, hi and welcome back to Advent of Code in Go day 17. Yeah, sorry for the delay, but I was away the whole day and therefore I couldn't make it earlier than that. Yeah, first before we start, I would like to talk a little bit or give a couple of words regarding the yesterday's puzzle. So this was definitely something that was harder than I expected. I wasn't expecting working 6 hours on some solution and in the end only get the first part. Today, in when I was on the train, basically I fixed the second part as well. So this is currently updated in the code that you can find in GitLab. So there is a working version also for part two. Um, but I didn't came to explaining the code right now. So this is something that I will do later, probably tomorrow, where we'll go through the individual steps for solving part two. And then I will also cut down the stream for day 16 to a couple from 6 hours to maybe two. I don't know. I will see where are things that I can actually cut away. I think that a lot of despair is probably not necessarily that interesting to see and to watch. So yeah, with that, I will hopefully make this tomorrow so that the solution for day 16 will be on YouTube tomorrow. Yeah. So, but this is something that will come. I didn't came to had the time to upload and cut it directly today. So, okay. So therefore, if you're interested in this and how it in the end was solved by me, you can see it tomorrow. So with that basically done, let's talk and take a look at our today's puzzle. So we have day 17 and see what we have to do today. Pyroclastic flow. Your handheld device has located an alternative exit from the cave for you and the elephants. The ground is rumbling almost continuously now, but the strange wells bought you some time. It's definitely getting warmer in here though. The tunnels eventually open into a very tall, narrow chamber. Large, oddly shaped rocks are falling into the chamber from above, presumably due to all the rumbling. If you can't work out where the rocks will fall next, you might be crushed. The 5 types of rocks have the following peculiar shapes, where hash is rock and dot is empty. Looks a little bit like Tetris, but with different rocks. Okay, the rocks fall in order shown above. First the minus shape, then the plus shape, and so on. Fall in the order shown above. Okay, once the end of the list is reached, the same order repeats. Okay, so basically in this order they will always come. Okay, the rocks don't spin, but they don't get pushed around by jets. But they do get pushed around by jets of hot gas coming out of the walls themselves. A quick scan reveals the effect of jets of hot gas will have on the rocks as they fall, your puzzle input. For example, suppose this was a jet pattern in your cave. In jet patterns, bracket left means a push to the left, while bracket right. Is this bracket? I don't know. Bracket, braces, I don't know exactly. Angular bracket, I think. Are these angular brackets? Yeah. If you know the exact terms, I don't know. Just write it into the chat. While right means a push to the right. The pattern above means that the jets will push a falling rock right, then right, then right, then left, then left, then right, and so on. If the end of the list is reached, it repeats. So, okay. The tall vertical chamber is exactly 7 units wide. Each rock appears so that its left edge is 2 units away from the left wall, and its left edge, okay, from the left wall, and its bottom edge is 3 units above the highest rock in the room, or the floor if there isn't one. After a rock appears, it alternates between being pushed by a jet of hot gas 1 unit in the direction indicated by the next symbol in the jet pattern, and then falling 1 unit down. If any movement would cause any part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused a falling rock to move on into the floor or an already fallen rock, the falling rock stops where it is, having landed on something, and a new rock immediately begins falling. Yeah, basically we are playing Tetris. Nice. Drawing falling rocks with add and stopped rocks with hash. The jet pattern in the example above manifests as follow. The first rack begins to follow, jet of gas pushes to the right, rocks falls 1 unit, jet of gas pushes rock to the right, but nothing happens. Rock falls 1 unit, jet of gas pushes to the right, but nothing happens. Jet of gas pushes rock to the left, but nothing happens. Rock falls 1 unit, causing it to come to rest. A new rock begins falling. Okay, jet of gas pushes rock to the left. Rock falls 1 unit. Jet of gas pushes rock right. Rock falls 1 unit. Jet of gas pushes rock left. Rock falls 1 unit. Jet of gas pushes rock right, and so on and so on and so on. The moment each of these next few rocks begins falling, you would see this. Okay, so basically these are the individual things that would happen just from this input that we currently got. Okay. To prove to the elephants your simulation is accurate, they want to know how tall the tower will get after 2022 rocks have stopped, but before the 23rd rock begins falling. In this example, the tower of rocks will be 3068 units tall. How many units tall will the tower of rocks be after 2022 rocks have stopped falling? Okay. From first, I don't think this should be that hard, actually, but I might be totally wrong about that. So let's see. Because basically we just have those patterns. We need to simulate how they fall in a real narrow thing. And it shouldn't be that much memory that we basically need. So I don't know why it should take that long to simulate that. At least the basic case. Okay, but let's see. So we have our... Okay, these are the rocks. No, we have our input and we have our rocks. Okay, then let's copy our input pattern and start working on our new program for day 17. So we have a new project which will be 17. Attach. And there we create a new Go mod file. We create our input file, our test input. And we create our new Go application, day17.go. Okay. So, how do we implement this? So first we would need some type of things that are basically our rocks, right? So we define an interface because we might have different we have different rocks, so with different shape. So now the question is, what is the interface that we actually need? So we would need to give it a position. Oh no. Rock are the interfaces. Okay, let's first think about, okay, what are the other types? So we have our different, so the H line, the vertical line, the plus, the, what is this? How do we call those? Minus shape plus, okay, minus plus, this is a L, it's not an L, but I don't know. The pipe and the box, I don't know, let's call them this way. So we use type H line struct type. What do we have? A plus. We have our type L. Oh, what is it? Yeah, just use L, which is not really. Maybe we come up with a better name later. We have our type, which will be a V line for vertical, and then we have our type, which will be a box. So what we need, what do we need as well? So we have our types that we basically our cave, right? Because we need to check in our cave how deep or where the rocks are falling. So So how does this cave basically exist? Or how do we need, do we actually need to basically, yeah, we just do the first easiest thing, and this would be basically to have the individual rows. So where we have our rows, which will be just of a shape of a slice of wool. I don't know if something is taken by a box or not. I don't know. We can also just think about, okay, we have the row and then each individual pixel is basically a pointer to our shape, to our rock basically that is occupying it. And if it's nil, basically we know it's not occupied. At least this is something that we can try. I don't know if this in the end makes sense, but we will see. Should be corner or arrow. Corner sounds good. I think we can use corner. Yeah, thanks. Corner. Good. So this is basically what we have. So then let's think about what we can implement there. So how would we now... do we need also the cave does also have a height, right? We should also have a height. And those height, which is an int, and it also has a width. Because we know that the cave has only a specific width in the end that we need for testing if something is in the cave or out. So now let's think about how we know where the individual rocks are positioned. So for that, basically the rocks would have some x coordinate, some y coordinate. But this is an interface, so therefore we need to implement them as methods. And so then we need to allow them to move left, move right, and so on. But these are things that come later. Okay, so now let's think about how to simulate that. So in the first step, basically what we would like to simulate is just have a cave and we create only one rock. Let's say we create one H-line and we would try to implement this that they fall on top of each other. So just as a first step. And see how this would work. So for that, basically we need our cave. Cave is equal a new cave. We know the width of the cave is, I don't know, what was it? 7? I think it was 7. Pushed by a jet. This is basically, we should also think about implementing this so that we can draw it. The rocks fall on the shown first 16th and so on and so on. If tall, it's 7 units wide. Okay. Each rock appears so that its left edge is 2 units away from the left wall and its bottom edge is 3 units above the highest rock in the room, or the floor if there isn't one. Okay. Okay, so basically we have our cave, which has a width of 7. That's a struct, of course. We did miss those things here. So we have our cave, which is width of 7, has a height of 0, right? And then basically we need to now keep things falling down. So let's say we have just, we create 10 of those horizontal lines and let them fall down and see what happens. E++. Oh, plus should it be. So within we just created H-line, which is of type H-line. And then basically we let them fall to cave. So let's say we have therefore a method move to ground or something like that. Oh, maybe we just implement it directly here. So we for true, and then we do something like move H-line down till it is fixed. So, okay, how do we do that? So I think this is now the important, the actual question. How would we do that? So for that, we can think about, so we know where H-line starts, right? So H-line starts, how was it called? Let's go back to the, after rock appears, No, this one is each rock appears so that its left edge is 2 units away from the left wall. So, and if we say the left wall is 0, then basically this would be 2. And its bottom edge is 3 units above the highest rock in the room. So we can say that the highest rock in the room will be the height of our cave. And therefore we can then initialize our position of our rock to be x equals let's say 2, right? Because 2 from the left. And y equals cave dot height. Okay, now hline doesn't have those attributes yet. So we need to implement this. So we have some x, which will be int. We have some y that will be int. Okay. So far so good, we can initialize that. So how would we now move down? So basically we disregard the jet for now. But what we can do is basically cave height +3, sorry. Needs to be +3. We need to move down until basically we hit ground, right? So we have different steps where we say always, let's say, rock, or not rock, hline dot move down. This is something that we can implement there. So we add this to the rock interface, move down. And then this move down needs to check if we hit rock bottom or not. So if we can move or we cannot. So therefore we should return something that is now telling us if it's fixed or not. Right? So therefore we need some bool basically that tells us, okay, this rock is now done. We are now settled because we can't move any further. So in order for deciding that, basically what we need to do is figure out what would be a possible rock that is basically below us. So, and this is where we need to know the individual fields here. So basically we need our cave to decide. So we need to handle over our cave. Move down, and then we can within move down check if we hit something or not. Maybe we don't do this as, maybe we do this otherwise. We move this to the cave and we move down our hline. So we change it. So where we say, okay, this is not a method of rock, but it's a method of our cave, because move down and we give it a rock. Yeah, this is of course wrong. We don't need to do it here. We just need to say we have our cave and we implement here, move down. So how would we do that now? So first we need to check which, if we look basically at our different shapes, and we always know the position of this shape is basically the bottom left. So we need to get from this shape which objects or which fields basically relative to its position are blocked by this shape and which are not. So because if we move it down, we need to check, for example, if something is beneath it blocking it. So this means, for example, if something for this horizontal line, it would be sufficient if any of those four are basically blocked, right? For something like these, only this one would be need to be blocked. And for this corner, basically, we would have 3 that must be blocked. Here it's only 1 that we check, and here 2. So therefore, we need to treat all those shapes differently. So which means that the shapes must tell us as a cave, basically, which are the relevant parts that we need to check. So, and this is something that we can do with our interface, basically, where we say rock and then get shapes, let's say, or get shape. Get shape. And how would we get this shape? Maybe we get it as a yeah, how would it look like? So we say it has a width and it has a height, each rock. So, and then also we can check if something is blocked. So if it's filled or not. So this is something that we can implement by that. Where we say, okay, we give an X position, or not X, maybe we I and J, no. Yeah, let's stick with X int and Y int. And this would basically tell us if this rock within this position is basically is blocked or not. So this is something that we then need to implement. So for example, for H-line, we need to implement this in a different way than we need to implement it for example, a corner. Okay, but this should work. We just see the exercise, not the code. Yes. Okay, thanks. So we have our rock interface, which tells us the width, the height of those, and if something is filled. And this is basically what we can use within our cave to check if there's something blocked, right? So if we know, for example, that the position of our rock, so we have different cases here. So in the first case, we know that the position of the rock is larger than our height. So if rock dot why doesn't it the non-bool value rock used as a condition? Yes, rock and then y greater. So if we know basically that this is greater than our height, we know we can always go down, right? Because there can't be anything that is blocked. No, +1. Height +1. So basically, if we start, then this is what happens. So our rock, why doesn't it recognize these? Because we don't. Yeah, okay. Rock y, unresolved reference to y, but rock has this y. Okay, so let's continue. So if we are further down, then we need to think about collisions, right? This is now the point where we need to think about, okay, how which parts within the individual rows are actually already been taken. So, which means we go through the individual rows where we currently are. So we go through the individual rows that we have within our rock. No, I think at the moment it would be sufficient to check No, we just go through it. So basically we start by the at the position of our rock. So for rock dot no, let's call them x, y, x equals, and not now we start basically at the position at the top left, bottom left position of our rock. So we initialize this with x. We do that for x smaller than rock.x plus width. So what we basically do is just checking for all our fields within the rock. If we go down, if there would be still space within our cave for that. So we just say rock.width. So because it depends basically on our rock, how far we need to check, or how many pixels we need to check. And then we do this for x, and we do the same thing for all our heights. So where we have y, and we do it for y, 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 and then the rock height, and y. And so it's a nested loop because we for every row we also do it for every single position. So what we now check is basically if there is any rock that prevents us from moving down with already in the cave. So we just check here cave c.rows, and we have y rows. Y means -1 because we want to go deeper. So if c rows y and then basically x not unequal nil, this means basically we can no longer move down. So if we already found within our cave a rock at a specific position where we would move later on, this basically means we are already done. So we can't move it further, then we basically return false, true, because we reached the end. So if we didn't find anything, this is still not 100% correct. This is something that we will fix later. But if we don't find anything, this basically means we can just move the rock further down one step, where we say rock.zh, or just say rock move down, which will basically just move down, or maybe we have some setter, or I don't know. We will see. Maybe we don't need those structs and make this a struct as well. and initialize yeah, I think this makes more sense. Okay, we will now change that. We will now make it these things fields so that we can set them. And then this is filled is something that we, this is something that we also need to check. Of course. And this will be then our fill, which is a slice of bool. And we don't need this. So basically, instead of rock, we just use here rock, y, rock. So, and we only need to check if something is, if something beneath is available. We only need to check this, basically, if this position is actually filled. So therefore rock dot fill from what is it? Fill from why do I have German? Is this this is strange. US keyboard, okay. Fill from X, no, from Y and X, but now we need to check that we don't need to be careful that we don't mix up the different coordinate systems. Because basically we have this internal coordinate system within a rock that basically begins in the down left corner and contains only, I don't know, 3 or 4 in those directions. And then we have this global X and Y coordinates, which is basically in cave space, let's say it that way. And we need to yeah, let's maybe rename then. So say always that M and X and Y is in cave space, and basically our coordinate system that we use locally will be M and N. So M will be then basically X minus rock dot X, and N will be Y minus rock dot Y. And this allows us then basically to have those different coordinate systems separated. So, and this means basically we check if the rock is filled at this specific position, and only if it's filled then we need to check if the row beneath it in the global positioning system, let's say that way, in our cave location, if this is basically then equals to nil. Rows is a slice of pointing to rock. So, and if this is the case, basically if there's a collision, we return true, and true will then basically make sure that this rock no longer has to move, so that we need to integrate it into our cave. If this is not the case, so basically we can go down. We basically just say rock Y is equal minus minus. We can just reduce it by 1, and then basically we go again, right? So this means if now fixed, then we need to integrate now our rock into our, let's say this is a rock, and we create here afterwards a different rock. So if this is fixed, this means basically we hit bottom, right? We hit the ground. So therefore we need to integrate this into our cave. So, and for that basically we have the current position, And what we need to do is basically make sure that our cave has now the correct height. Yeah, which will be basically the height of the position of the rock plus its height. And then set within the cave for each individual pixel that are these rows are stored within these rows, set if this specific pixel is blocked by this rock or not. So how do we do that? Okay, for first of all, we basically need to check if we need to create new rows. So, or we recalculate the new height. So new height will be then just the rock Y position plus rock height. Why don't we have this as a height? Okay, because this is still a rock. It's not a rock. Yeah, so it will be rock height. So this means basically if we currently don't have... but the new height should only be this, so... But if the new... For example, it could happen that the rock falls down to the right and we already have a higher height, then we shouldn't update it, right? Of course. So if new height smaller than cave.height. So we only update the height if this is actually smaller than bigger than the current height. So this means basically that we need to add new rows. So for, let's say, Y, which starts basically at height and we run until it's smaller than, as long as it's smaller than new height, and we increase it. So, and for all of these, cave height, dot height. So for all these things, we create new rows and append them basically to our rock, to our cave. So cave.rows append equals cave append. Man, this is something that I really don't get accustomed to. So, and we create a new row that will be basically a slice of pointers to rock. And this will be of size. What is our size? Let's define it here. Cave width. We already have this as a parameter. So we say cave width. Okay. Good. So this means basically we get our new cave rows. So, and after that, what we basically do is we go along all those. This is basically the same code that we need here. We loop across along the positions within the rock that are filled, and if they are filled basically, then we set within our rows that these not -1 but the cave, we set that these point to the new rock, these individual pixels. Cannot use rock as a type rock. Okay, let's do this. Okay, we always use this as a pointer. So this should mean that basically we store at the individual pixels within our cave which rocks are basically currently there. So now let's try to run this for a first time. So we basically need to see, or we would like to see what happens, right? So therefore it's probably a good idea to write some code that actually prints this out. So which means we have our, what are the okay, we have our cave, and the cave should probably get a function that allows it to print C star cave print. So how would we print that? We basically go through our rows that we have. So for rows, for row, comma, row index, comma, row in range from C dot rows. So, and now we loop over the individual rows, individual columns within each row for C, comma, rock, a column in range. Oh no, we do this basically by let's, yeah, I think we need to do this differently. We should use a custom loop index, so where we loop about over y and x, so to make it more clear what we are actually doing. So, and we start not with the first row, with the zeroth row, which will be the bottom, but we start with x, with y, which will be basically the height of the cave. Okay, c dot height. And this will be then but this is not true as well, because we also need to print afterwards. Oh, but we will change that then. So first print only the cave. So we have our, we start at the height, -1. Then we do this until y, or as long as y is equal greater than 0. And we increase y step by step. So then we basically loop over x, which will start from the left, and we say x will be smaller than the width of the cave, and we will increase x from time to time. So, and then format print. So if we now we check basically if this is already filled. So if the c dot rows from y and then position x within this row, if this is equal nil, which means it's a free a free field, then we print out a dot, else we print out hash. So, and after each row, basically what we do, we print out \n. So we make a line break. Format print line. Okay, and then we go backwards here, so we need to decrement y. So this should allow us to print the cave, but what it doesn't print is basically the current row, that the current rock that is falling down, right? So this is something that we need to print on top. So for that, basically, we need to figure out which height we actually need to print. So, so therefore, it can be that this new, let's say that this new rock is higher above the cave, so higher above the height of the cave at the moment. So which means that we need to adapt the height. So the height that we print will be basically the maximum. So we can say c.height. We initialize this with the height of the cave. But if we know that height is smaller, then, and for that basically we need our rock. Our current rock. So if this is smaller than the rock y position plus its height, minus 1, this means that the height will be equal rock y plus rock dot height minus 1. So, and now we print it in a different way. Basically, what we do is first we check if there is a row for this one, right? So if, because if the new rock that is falling down is above the height of the cave, it might be that there are currently there are no rows for the cave. So therefore we need to check if this is actually in there. So if y smaller than c dot height. So this is the case basically where we can do this, where we can just print basically the individual cave. So, but we first need to check. We need to print the rock. So we loop over the individual width. So, and then if c is larger, so first we need to check, I think, so we should see if we basically should render the rock. So if for this we need to calculate our m and n, which will be basically the rock position, the rock x. No, this will be basically our x minus the rock x. And for n it will be basically the same, so our y minus rock dot y. And then we also need to check if these are valid coordinates within our rocks. So if m greater equal 0 and m smaller than rock dot width, so this must be true, and n must be greater 0, so that we basically are within the valid local rows that we have for our shape, and n will be smaller than rock dot height. So, and if this is then the case, we also need to check that basically this is some icon, that this rock is filled at this position. Rock.fill from n, n. So if this is the case, then basically we print out this add symbol. Print add. So if this is not the case, then we now need to consider the other cases. So the other cases might be that either we check if this, basically we check if there is already at this position, there is a row, right? This is something that we know if the y coordinate is lower than the height of the cave. This means there are rows. And we need to know if those rows are basically not empty. If they are not empty, then we print out that there will be rock. Otherwise, we just print empty space. So, and this should allow us to print the cave together with the currently falling rock. So, let's see what happens if we do this step for step. So, we have here our case where we create a new rock and then move it down. Let's see how it works. So we do cave.print and give it the rock, and then we sleep for 1 second. So now let's see what happens when we try to run it. I think what we missed so far is initializing our rock correctly. So because our rock currently has, okay, build did succeed, but we did miss out that this rock also needs the width, the height, and the fill. Okay, so for our rock, where we said, what was the first one, the H line or the horizontal line? Yeah, the horizontal line, where we know, for example, the height of the horizontal line is 1, the width is 4, and the fill will be just a slice that will contain a slice of true, 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 and true. This is correct. Missing expression, yeah, slice of bool, or slice of bool. So, right, because it's basically, these are the lines, and then each line contains individual items. So we have only one single line, and this single line contains 4 different fields that are always true, because within this line all fields are actually true. So now let's try to run it and see what happens. Yeah, stop and run. Okay, this doesn't do anything, which is not what I expected. I at least expected something to happen here. If it's fixed, basically we append it, and then we should also break, right? We should also end our final. But this is probably not the thing. So let's debug it. Let's go into it with the debugger and see if what we did is actually sensible, or what actually happens in where. So we have now our rock. So, and our rock has the x position of 2, the y position of 3, the width of 4, the height of 1, which looks quite okay. This is our fill definition, which is also okay. So we go into move down. So let's check. First we check if the rock Y position is greater than the height of the cave, and this is actually true, then we just return false. I suspect that there's something that we missed to implement here. So if this is, because at this point we are quite sure that this, we can just move it down, right? We can just move it down. Because this is the case where we basically need to check for collisions, and in this case we don't need to check that. So therefore nothing happened. Now let's try again. Moved out. Oh, sorry. So we move down, return false because we're not fixed, which means we can print. We don't print anything. Okay. And we sleep 1 second and we go again. Go print. Okay. Let's go down one more. Now we need to check for collisions. So we now check for the individual rock. So what do we have? N is M0 and N is 0, Y is 1, X is 2. So, and we don't have basically our row 0. Because currently we don't have any row. So I think there's some issue there. So how do we do that? How do we check for this? Height is initialized with 0. Is this correct? The cave height? How do we initialize the cave height? With 0, yes. Then this is not true. Let's try again. So because we run through it. Oh, let's first start this print, right? Fix this print. Ah, of course, we should. We calculate the new height, but we don't use it. Okay, this is a dumb mistake. So, and maybe then at the end we print out also some separator. Print line, so that we know when a new line will begin or a new cave printout will begin. Okay. This doesn't look so bad, right? So we start here, 3 rows above, then we go down 1, then we go down 1, and then basically we're run into this index out of range, which is what we expect, right? Because this -1, if we don't have any rows, this is definitely not correct. So this is something that we need to check here explicitly. So if y -1 equals, if y -1 equals, what should it, no, if y equals 0, then basically we also should return true. So therefore, if this, or so we either reached our last line or the bottom line, let's say it that way, or we see that we somehow fill a position that we filled before. Okay, then now let's run again. It falls, it falls, it falls. And then we start with a new one. Okay, but it doesn't seem to update basically. Let's print also the line number at the beginning when we print it out. Format print %d, where we say this will be 3, and we use y, printf. So what we are now seeing is basically that this mechanism which should stay, keep basically this one and make sure that it's fixed, that this doesn't work. So our fixed method is currently not correct. So which is happening here. So therefore, let's see what happens in here. So we go down and now we are fixed. So which means now we have our new height. We have the new height will be 1, which is correct, right? Because we basically have a new rock and before we had height 0. So if the new height is greater than the cave height, which is the case, we go in there and we append a new row to our cave row. So now the cave should have one single row, which is correct. And all of those fields in there are nil, which is also correct. So now we basically go through our rock positions. We calculate the individual positions in our local files, local system. We check if these individual things are basically occupied, and then we set our y and x coordinates and we assign them to rock. So this means now this pixel is blocked by this rock, and another one, and another one, and another one. So within our first row, we should have now 4 fields which are basically blocked by our rock that we had before. Okay, so far so good. Which means now we can break. We can break. Now we create a new rock. We start it at Y position, which will be now, at least it should be somewhere else. The Y position should be now at, since cave height is, why is cave height 0? It should be 1. Maybe we updated the height, right? We did, at least I thought we did here in there. How can that be that our cave height is 0? Ah, we don't set it. We just, okay, we just calculate it, but we don't set it. So therefore we need to set it as well, where we say cave height is now equal than new height. Okay, let's continue. So we set it. Ah, okay, we need to restart. And we run. Ah, now it works. And as we see, basically, we always start there and we pile up H line above H line. So we always start 3 higher. So this seems to work, which is quite nice actually. And this will take not forever, but until we have stacked 10 on top of each other. Okay, nice. So now let's do this with a different set of symbols. So basically now we need to implement all the other symbols. At least when I remember correctly from the puzzle, we should always rotate those different shapes. Yeah, and initialize them from different things. So therefore we create a new method, a function which we call create rock. Create rock, and this will takes an index or the number, let's say the rock number, which will be an int, and it creates a pointer or returns a pointer to a rock. So now as a first start, we basically just create our rock here, which will be our horizontal line. Rock equals create rock. And then we put in the number, which will be just I. So the number is something that we can use to decide how the rock will be shaped. So basically what we can do is now we have, we need the cave height. So we say here, create rock, and then we say height. I know, we give it the number and we have the height or the cave, I don't know, no, just the height. The height, and the height will be then height. Where was it? Create rock, cave.height plus 3. Okay, so and now we can do some switch case. So where we do switch on the number modulo the number of different shapes that we have. So we have 5 different shapes. So now we have in case 0. So this is basically then our horizontal line. And then we initialize the rock, the height to be 1, rock.width to be 4, and rock.fill to be this value here. Okay, and now we need to do this for the other cases as well. Do we need a break? I don't know if this is something that we actually need here. And in the end, we return our rock. So in case 1, we have this plus, right? And the plus has the height of 3 and the width of 3. And then basically we go through the individual lines and say what is filled, what is not. So we have 3 different lines, and within these basically just the outside, the corners are always false, so they are not blocked. In the middle, all 3 are blocked, and then again in the corners there are no blocks. So this for the plus, which is plus. Now let's create, what do we have, this corner. Now we have our corner plus corner where rock height and width are all 3. Then then basically our baseline, we have true, true, and true. And then basically for all others, we have false, and only the last pixel is true. Okay, there's some question. I recently started learning Go. How would you explain when and how to use pointers? I mean star and the address handle. I'm always confused. I've always been doing JavaScript. Yeah, this is some definitely confusing topic for me as well. I ran into a lot of issues in the past because of the tendency of Go to copy always the object. So if you don't use pointers, and since I was also using other languages before, so where you most of the time you just copy references, so you have things like pointers basically. This made it easier for me to always use pointers, because then I know when I create a new object, this will be this object, and it's not about the copy that will be done somewhere, especially if you have to deal with arrays and you assign arrays to a different copy, and then at some point these arrays get shared, so you change one object but it changes also a different object which incidentally uses the same array. So therefore I would always try to use pointers as a general rule. I think there's also some general rule usually that this is easier to do that. Yeah, how would you explain when and how to use pointers? Yeah, for me, I would always think about that. I would always use pointers if I want to know what are the individual objects. So for everything that looks like a value, where you don't store arrays, where you just have, I don't know, a struct with two fields that are both integers or something like that. For these things, it's fine to have concrete objects, so to use the structs directly. For everything else, which is more complex, which contains maps, which contains other containers or something like that, I would always prefer pointers, actually. So always define them. So for example, here, when we look here, right, this rock is something that we could use as a copy, right? But nonetheless, I try to, not copy all the rocks. For me, it's fine if I create one rock at a time, at a specific time here, and I just pass around the pointer to this object. This is, for me, easier to understand than when I would have a rock object here that would be copied every time I assign it or I use it as a parameter and so on. So for me, mentally, I would always prefer, not always, but most of the times I would prefer basically pointers. I don't know if this helps you, but at least for me, if you're coming from a different language, then I think the model with pointers and using pointers more is way easier to understand and to adapt to than trying to have these objects that are automatically copied. This is something that comes from the C++ stuff, and I don't. Yeah, I'm not that fond of that. So I think this might be really useful if you have to create a code that is highly efficient, and so. But most of the cases, I think at least as a beginner, using pointers is probably easier and less error prone, because it's less surprises to me. Okay. Will the compiler tell me when to use them or when I'm doing it wrong? Yeah, the compiler will tell you basically just when the type is not correct. So when you should use a pointer but you're using an object or something like that. This is something that the compiler will tell you. It doesn't tell you when it's a good idea to use a pointer. So I don't know. I can't tell you exactly. But I think it can be helpful. So usually the compiler, at least in my opinion at the moment, is quite good. So all the errors that it shows to you before you actually run this, especially if you have a decent IDE. At the moment I use Goland. This is actually quite nice, and I'm currently on the trial edition, but I'm thinking about basically buying it because it's really helpful in comparison to what I used before. So therefore, and I'm not an expert in Go as well, so I'm still also learning. So therefore, I think that at least the integration here in Goland is quite decent and quite good, and there the compiler is definitely helping. Okay, so going back to our code, so we have our corner. Now let's build our vertical line, which has a height of 4, has a width of 1, and basically we have only four lines in there, which are always of width 1, and they are always true. Good. So, and now the last one will be our box, which is basically 2 by 2 and consists of 2 lines with 2 values. So now, if we now run this, we should already see basically the different types that are coming down. So let's try to see, can we move this? No, we can't move this. This is actually not that nice. I was hoping that we can scale this. So run it, and now we should see, okay, the first one is basically our H line, then the plus, okay, then the L, then this vertical line, and there we have an error. Okay, so there's something going on in our code which basically does the collision detection. Runtime error, index out of range with length 7. Let's see where it actually crashes. With range 7 with length 7. Index out of range with length 7. Where could this happen? What could be here? 7 is the question. Maybe we should I assume that one of those is probably wrong. So this is row 7, index out of range with length 7. Okay, I think I get it. Because now we have the point that this will go down further. And therefore we go inside here, but we check rows above. So we check rows 8 and 9 and 10 for collisions, but we don't have them within our cave. So, and therefore, if we don't have them in the cave, it's this check basically breaks. So we need to make sure that we only check here if basically we already have a cave. So if there's already a cave. So this means that we need to check if y is smaller than cave.height. We have our C. So we only need to check if we have this if we are basically checking within the height of our cave. So, because otherwise we have here these problems. Let's run again. This works not. Okay. There's probably some off by one error. Okay, now the L falls. Now come the important parts. Yes, this works flawlessly. Nice. Now we start again with our horizontal lines. Now the plus. Okay. Okay, and it goes up and up and up and up and up. Okay, so far so good. So I think this seems to work. So where we actually moving down, this is something that where we can check mark on it. So moving down those things and they pile up and they fall next to each other and so on works. So let's check what are now the next problem. So now we come to those jets that basically push the rocks around. So for that we need to read this pattern basically from our input file. And this is quite easy, but then we need to move them to the left and to the right, and we need to check if we can move them, right? So we need to check if we are within the bounds, and we can't move them to the left, or we don't move them sideways into another rock that is already within the cave. So let's first start with basically reading this pattern. So we have our we already have our test.txt pattern. So let's start reading it. So we have our input file. We get an error. We open our input test.txt. So if we have an error that is not equal nil, then basically we just panic and we defer our input file close. Good. So from this input file we read a couple of moves. So we have our we can read this. I think there was this read file, right? We can directly read this into a string. Yeah, I think this is more helpful. We directly read this and we return our, let's say, jet pattern. Jet pattern string, I don't know. Which is already a byte. So then we need to convert this to a string. Pattern bytes. So jet pattern string, which will be just jet pattern bytes, and we can just, I think, did this work? I'm not 100% sure. Can we convert the bytes directly into string, or how does this work by casting? Yeah, it seems to work. Nice. And now we basically split it. We pass it into a list of actions, and those actions are then I think the string is okay. just patterns. Jet patterns. Okay. So, and then basically what we need to implement is a function that takes the pattern and tells us what to do. Or basically, we call apply, not it wasn't moved down, but how do we call it? Cave apply jets. Let's just say apply jets. And this is something that we only do to our current rock. It's something that we also need to, we need the cave for that, because we need to check if we run into the cave width or if there are some other parts that are already in the cave. And we have for that, basically we have our jet counter or index, which will be the int, and we have our jet patterns, which will be the string. So this means we need to check in which case we move down and when we move to the left and to the right. This is something that I currently don't know yet. We will see. So how do we do that? So basically what we need to decide is first if we want to go to the left or to the right. So, and this is something we can do quite easily because we just get our character that will define if we want to go to the right. So this means our direction will be basically the jet patterns. And then we index it by the jet index. And this jet index modulo the length of the jet patterns. So this means we always get a repeating pattern, right? And this should then be basically just a angular bracket to the right or to the left. So, and then if direction equals this, we basically mean we know we can do this, move the rock to the right, otherwise we need to move it to the left. So, and in each of those cases we need to consider what can happen, right? So, let's first start with that. If we move it to the right, this means basically we need to check if everything that is right from the pattern is free or not. So this means, for example, if we are directly at the right of the cave, so then at the right side of the cave, then we can't go any further, right? So if, let's try to figure out the conditions. If rock.x plus rock.width -1. So this means this is basically the coordinate of the rightmost position of our rock. And if this is equals to our cave width -1. So this means if we are already at the rightmost side, basically then we don't do anything. So if we aren't, this means we can move over. So therefore we need to check here if we can move to the more to the right. So, and this now depends basically on what is will be right of our object. So here we need to do the same check that we do basically for moving down, right? So we need to check, where is it? Move down. Maybe we implement something like move right and move up and so on. Yeah, I think this makes sense. So we copy that, and now we try to convert it to something like move right. So, and now we copy this over and just do something like c.move right from rock. So this means if we are directly at the right, then we can't do anything. Otherwise, we need to go into our method here. And our move right doesn't keep something, so it's not fixed afterwards. So, but what we do, basically, if we can move right, we increase its X position, right? So this is the easiest case right now. So if we know that we are above our height of our cave, then we know that there can't be any other rocks that we might collide with, right? So therefore we don't need to do anything in this case. If we are within the height of our cave, that means that we have some other rocks left and right possibly of us. And then we need to check now the condition if we can go to the right. And this is something that we need to check for all. Can we check this? Yes, I think we can check this by just looking if when we go to the right, if the X position +1 is blocked or not. So we check if Y is smaller than the height. So basically we loop again over all the fills within our rock. And then we check if the if we are directly within the height of the cave. And we check if the field right to our field that we currently have, if these are blocked. If they are blocked, if one of those is blocked, then we can move. So this means can move equals false. Oh, at the moment we assume that we can always move, right? We assume we can always move. So can move is true. And if we detect that to the right of one of our blocks that are filled, there is already some block, then we say that we can't move there. So we say can't move is equals false. So, and we only move to the right if we actually can move. So if we can move, then basically we increase our rock.x ++. We increase our x coordinate. Okay, looks quite easy. So let's see what happens when we try to apply it. So move right. We ignore the case for move left at the moment. But then the question comes, in which order do we need to implement these things? So let's see. The rocks don't spin, but they don't get pushed around by jets. The rocks falls in the order shown above. First, oh no, these are other things. The total is exactly... after rock appears, it alternates between being pushed by a jet of hot gas 1 unit in the direction indicated by the next symbol in jet pattern, and then falling down 1 unit. So, if any movement would cause any part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused a falling rock to move into the floor or an already fallen rock, the falling rock stops where it is. Yeah, okay. So this means basically we have to do this before we actually move it down. So this means we call here cave dot apply jets to our new rock. The jet index is basically our counter, E. Oh no, it's not the E. Basically, it's the individual step. So we have our list of steps. Step will be 0. Let's start with step 0. Apply jets, rock, and the jet index and our jet patterns. Jet patterns. And then after each of those steps, basically we print it and we increase our step counter. Okay, let's run it and see what happens. So it moves to the right, it moves to the left. No, it moves to the right and right again. Ah, we can only move to the right, correct? These should all go to the... At least there are one. Maybe we should print out actually what should happen. So this is hard to see. Apply jets, and this apply jets will then print out format.print line, move to the right, and move to the left. Let's try again and see if this move to the right, move to the right, move to the right, move to the right, move to the right. Okay, there's something funky going on because we have in parts multiple move to the right, which doesn't look correct. How can this happen? Ah, because we break here. We will see if this fixes this. So, but first maybe implement move to the left. So move to the right seems to work somewhat. Let's see what happens after move left. So basically the same principle as before, but now we need to check not the right bound, but the left. So if, for example, rock x is equal 0, then we know greater 0. Then we can only move to the left, right? If we are already at the left on border of the cave, we can't go any further. So this means here we don't need to check our x plus 1, but our x minus 1. So, and this means we need to check that basically x we need to check a new condition that x is greater 0. No, x should not be... Ah, no, I think this is already fulfilled because x is always 1, at least 1, and therefore we always run starting from x, therefore this can never be negative, so therefore this should work, and we can just change it here with one condition, and this should be it, basically. Let's run it and see what happens. Ah, we should also call the method, the function. not just write it. So within our apply jets, c.move left for the rock, run it, oh, move to the right, move to the right, move to the right, multiple move to the right, move to the right, move to the left. Okay, it moves to the left. And we go down, down, down. Move to the left, move to the left. There's a lot move to the left at the moment. Move to the right. Move to the right, move to the left. Okay, but as we see, basically, it's not that straightforward that we only add it into one direction. Okay. So far, so good. So this seems to work with our move to the left, move to the right. Now let's check what we actually need to calculate in the end. So we can push them down, we can push them up and so on. Does this actually look like what should happen in the end? Let's see. I think there's something wrong. The first rock. So if we compare, here jet of gas pushes to the right but nothing happens, rock falls 1 unit, jet of gas pushes rock right but nothing happens, rock falls 1 unit, jet of gas pushes rock left. This is what should have happened. But I think in our case, this left is not happening. At least our things is not pushed to the left. So let's start to the beginning. Okay, this is to the line buffer. Let's just do it for the first 4 rocks. So we started, move to the right, move to the right, move to the right, and then move to the right, move to the right, and this is something, there's something broken. There should be this move to the left, right? Move to the right, move to the right, move to the right, then there's a move to the left, but this is something that we don't have here. So something is going wrong within our jet patterns. So one move right, move right, move right. This should be moved to the left. Okay, then let's debug into it, right? So we have this, and we know in which direction these should be called. So let's debug. So first call, basically, we get our jet patterns, which look like the file. So this is fine. So we get our direction, which should be okay. Let's maybe create a rune out of that. This is probably easier to interpret. No, it's not. So we say it's move to the right. Okay, this is correct for the first 3, right? Jet index is 0. So next, we go in there. Jet index is still 0, which is wrong. So, which means, why is this still 0? Step plus plus. Step. This should be step and not our index of the rock. So let's try again. Oh, let's maybe see again. So move to the right, move to the right, move to the right, move to the left, left. What? Move to the right, move to the right, move to the right, then move to the left. But why twice? I think this move to the left seems to be wrong. I don't know yet why, but there's something fishy going on. Move to the left. This should update basically our X position. Let's debug into it. Move to the right, move to the right, and now we are move to the left. So we know we have our rock at X position 3, at Y position 0. We know X is greater 0, therefore we can move to the left. Y is greater equal height. It's not, therefore we need to check. We go into the individual. Okay, now we calculate the positions. Okay, this is fine. If y equals 0. Okay, I think this condition is something that we need to remove from our from our move left and right, because even if we are in the below, we can always move up and down. We don't have to check for this y condition that was only used for move down, basically to guard us against this case. So, but this is a case that we don't have because we are looking in the yeah, we are currently looking into the, yeah, okay. Let's see again. We are currently looking only in the row where this is possible. Aha, and there we see the move to the left did succeed. There are still 2 move to the lefts, which is still puzzling. And I think this is something that we need to check. Why? So basically we apply the jets. Then we move down. Then, we have this break here. And this break basically goes here, applies the same jet again. No, basically it does not. It creates a new rock and then directly applies the same jet. Okay, this means we should print at the beginning and also update these things. So we print it, we apply the jets, we run through a step, we increase the step, and we sleep 1 second. So let's run it. To the right, to the right, to the right, to the left, and then nice. Okay, this looks better. Now let's compare that basically to our browser. How does this look in the end? If we compare it this let's copy that and compare it to what we find. Test the result. No, we don't want to edit. And then compare. So then basically we see, this looks exactly what we are calculating. So we can be somewhat sure. So let's see again. How long does this work and what is the... To prove the elephant of your simulation is accurate, they want to know how tall the tower will get after 2022 rocks have stopped. But before the 2023 rock begins failing. In this example, the tower of rocks will be 3,608 units tall. Okay, this means basically we need to simulate for 2022 rocks. Let's do that. And then basically we print out the height of our cave, and then we should be there. Format.print and printf height of cave at the end e \n and then cave.height. So, and now for that, basically we probably better uncomment or comment the printing of our debug information, because this might get a little bit noisy. So just run it, and it runs, it runs, it runs. Okay, it runs and we don't know why does it run so long. There's definitely going some problem. Okay. Why doesn't it work? So let's print every time we basically create a new rock, which should be still plenty of. Ah, of course. We still have the sleep in there, right? So therefore it takes ages. This makes sense. Get rid of that and run it. So height of the cave at the end 3068, and our elephants think it's 3068. Okay, so this means basically our toy example calculates to the same result that we should get. So now let's get our real input puzzle. Oh yeah. This is a lot of information for controlling, and create our new input file. And then and then basically read our input from here and calculate it again and see where we end up at 3147. So let's check if this is the solution for our first part. Yes, okay, so our Tetris simulator seems to work. Nice. This is a nice addition. Okay, and now the elephants are not impressed by your simulation. They demand to know how tall the tower will be after one... I don't fucking know. What is this number? 1 trillion. Is it? So 100k, 1 billion, 1 trillion. Okay. Just for fun, let's see how... No, but this is something that we can't simulate. Now we need to prune basically our grid. We need to throw away the rows that are no longer necessary. But the question is, how do we know which rows are necessary? Okay. I'm not sure that I should continue today. I think it's late enough and we came to some success, so I will probably continue with this puzzle tomorrow. I need to think about it, but I think the only option is basically to remove all the rows that are no longer necessary because we can't reach them from the top. So, and then you are basically left with a fixed set of rows that might be, I don't know, 100 rows or I don't know how many. And then we can throw away all those rows that come way below, and then we can simulate these things. But this is something that needs some major rework at the moment, and I think it was a long day for me. Therefore, I'm not going to finish this now yet. So, but there will be then a second video basically about part 2. I think this is the correct way now. So, yeah, then thanks everyone. I will push the code to GitLab so that maybe you can take a look at that. And yeah, maybe see you tomorrow then with part 2 and maybe also the other puzzle. So for day 17, 18 already. Okay, bye everyone. Have a good night.